Okay, good afternoon. My name is Jack Weiss, and today I'll be presenting Deep Network for the integrated 3D sensing of multiple people and natural images. So the problem is we want to find and localize multiple people in a crowded scene, and also figure out what their shape and orientation is. And this problem has application to autonomous vehicle navigation as well as industrial robots, delivery robots, and service robotics. So the basic objective is to take a 2D image of one or more people, and we want to automate 3D position and shape estimation from that 2D image. So here are some of the challenges. We may have multiple people of different sizes and shapes and depths. We have various activities of people. They could be walking, running, and orientations. They could be facing the camera, facing away from the camera, doing other activities, reaching, dancing. And we also have occlusion, so that things could be occluding the people as well as people occluding other people, so we have to deal with that as well. So the depth ambiguities, as you can see here, sometimes we have larger people that are further back and smaller people that are closer, and so those will look about the same size in the image. And then also with things like steps, we may have people at different elevations within the image. We also want to formulate a single cost function for learning to simplify learning, and we want an integrated learning process so that the various algorithms all work together to produce the final solution. So this solution is a feed-forward, multitask, bottom-up solution for localization with 3D pose and shape estimation. It identifies human body structures, that is the human body joints, and groups people based on 2D and 3D information. This 2D and 3D data are fused using learning scoring functions and aggregates the solutions into a 3D skeleton hypothesis under kinematic tree constraints. So here's the basic approach. We take a 2D image with one or more people, and then we find the 3D skeletons, and we need to predict the 3D skeleton shape that's based on the original image. And then with the representation from the original image and the 3D skeleton, then we produce the essentially mesh 3D volumes of the individuals in the image in 3D space. So our approach is we want to find the skeletal joints. This is the basic approach, and detect body joints by their type. Then we want to solve a global optimization problem to join these body joints into limbs, and then find all connected components under the kinematic tree constraints. For ground truth, we need both the 2D imagery as well as the 3D aspects of the skeleton within an area, so we use motion capture. This is the CMU Panoptic studio, and it's about 13 feet tall, so you can fit multiple people in there doing activities. It has 480 VGA cameras embedded into the walls, and it has 11 Connect depth finding cameras in order to understand the depth of all the activities going on with all the people. And this captures ground truth of imagery and the 3D volume, and you can record various group activities. So here's our computational pipeline. We start with the deep feature extractor, and that is a typical convolutional neural net, and that extracts our initial representation from the 2D image. Then we have a deep volume encoding, and this is where we encode the 2D and 3D skeletons of the individuals found in the image. And this is where we have our first loss, our encoding loss. Next, we have limb scoring module that identifies different human body joints hypothesis and connects the compatible ones. And that has our second loss, our limb loss. And then we have a skeleton grouping that uses binary integer programming, and the skeleton grouping groups multiple people under kinematic constraints. As you can see in the image above that, we've grouped the various people from what was the skeleton hypothesis, and then the final is a 3D pose, decode, and shape estimation, and that's where we get our final solution of our mesh shapes of all our people in 3D space, and we also get our final loss.
Did you put the losses? I thought you put losses here. For each loss, you put the equation. What is the loss? Encoding loss or limb loss?
Yeah, we'll those will be in the. We'll be getting to those losses. So the deep volume encoding inputs image features and encodes ground truth 2D and 3D skeletons. This is based on the human 3.6 million data set used for 2D and 3D physiology. It's a total of 17 joints and 16 limbs and a kinematic tree of connected limbs. So this is how we do our deep volume encoding. So the basic idea is from within a motion capture, we need the 2D image of the motion to be captured. And then we also need the 3D information from within that motion capture in order to encode this. So here's the process. We want to associate a slice, basically a column, in the volume for each of the joint components. Yeah. So we want to associate a slice of data for each joint, for each person within the 3D volume, and this encodes the 3D skeleton associated with the person.
But we don't see the cursor. Where is your cursor?
I see it on my screen.
You see it?
Does it need to go off the screen? Oh, here we go. Here we go. There we go. So we encode for each joint, for each person, we encode all the 2D and the 3D information for that skeleton for that joint. So that is actually fairly redundant data, but what that does, that allows us to learn what these various joints look like in 2D. It allows the algorithm to learn what these joints look like in 2D at various angles and at various distances for various size people. So the entire skeleton is encoded associated with the pixels for each one of these joints for each person. And this is how the encoding works. So the deep volume encoding mechanism is a multi-stage loop. Where's my cursor? Okay. And so we have the image features coming in, and we have the previous, from the previous loop, 2D prediction from the previous stage, and this updates our 2D encoder, and then the output from the 2D encoder and the 3D prediction from the previous stage and the image features all go into the 3D encoder, and then finally from that the current 3D representation gets output, and then the final output from this module is the image features, the 2D representation, and the 3D representation all concocted together.
And you can get rid of that thing. Next,
So this is our first loss. And this loss is the square Euclidean loss between the 2D prediction. This is the square Euclidean loss between the 2D prediction M here and the ground truth. So this loss gets summed up. And then we also have the mean per joint 3D position loss between the 3D predicted, between the 3D predicted and the 3D ground truth. And this gets summed up, and then both of these get added together, and this is our encoding loss, which is our first loss.
I mean, it's not necessarily encoding now, it's just a loss to get the 2D joints and 3D joints.
Okay. Loss
Not
of...
loss, just loss.
Okay. So in order to map all skeletons, we need to detect potential human body joints and their types in the images, and we need scoring joints using trainable functions. And then we want to find all connected components satisfying strong kinematic tree constraints, with each component being from a different person. So where we are now is we're reaching the limb scoring. So the limb scoring is we extract joint proposals using non-max suppression from volume 2D maps. Each joint proposal has a type, elbow, wrist, knee, etc. And we list all feasible kinematic connections. Then the limb scoring network learns scoring via multiple convolutional and ReLU layers to build a limb map. This limb map is combined with 2D input map to form the limb list. And then a fully connected layer with softmax regression to do the final scoring. And here we get cross-entropy loss as our second loss. So the binary integer program with constraints, this is how we're going to map our skeletons to the various people. And so we have 3 constraints. The first constraint is ensure that every connection component falls on a single person. Second constraint, ensure that connected components select at most one joint. And then the third constraint is the connected components are all as large as possible. And we encode kinematic constraints by iterating over all limbs. This is our people grouping as a binary integer program problem. This is the equation. And so we want to estimate the optimal M star such that the graph abides by the 3 constraints that were in the previous slide. We want to compute L star equivalent is equivalent to finding a binary indicator X as an element of the binary set L. And this can be written as a row-by-row sparse matrix A as an element of the binary set such that AX is less than B, where B is the all ones vector. And finally, we get to the 3D pose decoding and shape estimation. So in here, we take the skeletal grouping and the image features, and we're going to decode the 3D pose, which is here. And then we're going to use an autoencoder to get our theta and beta values, theta being the rotational angles for the skeleton, and the beta being the dimensions for the 3D mesh. So initially, given the feature volume of a person and its skeleton, we want to learn a function that attempts to different regions in the 3D map to decode the position of each joint. And we do this by selecting various points along the limb. So we sample multiple points along each limb, and the learn function assigns a score to each sample as well as the joints. And then the final predicted 3D skeleton is the weighted sum of the 3D samples. And here the loss is the position error from ground truth. And this is the first part of the third loss. Third loss has two parts. So next, now that we have the skeleton, we need to build a 3D model of the person. So the skinned multi-person linear model is a realistic 3D model of the human body that is based on shapes from thousands of 3D body scans. It is a mesh with about 7,000 vertices and accurately represents a wide variety of body shapes and natural human poses. So what we need in order to build the 3D mesh of the individual is we need the joint angles, joint angle rotations, theta, and the body dimensions, beta. To do that, we use an autoencoder in which the input is the 3D skeleton, and then the autoencoder recovers the theta, the pose parameters, and also the beta shape parameters. And then the loss is the error between the input and output of the autoencoder. And the paper didn't specify exactly, but it seems that this autoencoder could be used because it reduces down to the minimal representation of the mesh shape with those values. But it wasn't exactly clear as to the theory behind it. So that's our final solution for 3D pose and shape estimation. So next, the analysis of the learning. This is for 100 images, and we can see that the limb scores versus number of components, and these are limb vector components. The limb scores are getting pretty close to the optimal solution of 0 and 1. And this is the binary linear integer programming solver. And the nice thing about this is that it's linear growth in time versus number of components. So we can see that it's not using excessive CPU in order to solve. And for our quantitative results, this is the human 3.6 million data set. And what we're looking at here is the millimeter mean joint position error for each action of 15 actions. And we can see that MovieNet is getting better results. Smaller numbers are better pretty much across the board on all 15 actions than these other previous methods, with a final mean score of 60 millimeters versus 69 and 73 for the other solutions. On the human 80K data set, MovieNet has beats the other score, and with the intention mechanism, we're able to get an even lower score. And the attention-based decoding improves performance by simply averaging the 3D skeletons at each 2D location. That's how the attention gets the better score. And for the CMU Panoptic data set, the fine-tuning on the CMU optic data set, which had close to 75,000 samples, was able to achieve much better scores than the two other, where's my cursor, than the two other previous solutions, and did quite a bit better than non-fine-tuned MovieNet. And these are different group activities, essentially games, haggling, mafia, ultimatum, pizza, and then the mean values. So qualitative results, we can see that we have multiple people with people further back that are being detected fairly well, and there aren't many, well, there is one artifact in this, and we can see that this leg seems to be clearly bent quite a bit, this knee, but in the individual skeleton it's not so much. And here we have the same problem with the knee being bent to, looks like it's parallel to the ground. In the skeleton and the mesh model, not so much. Dancing, we have a situation where the arm looks straight for the girl here, but looks fairly bent in the mesh model here. Skiing, the only real artifact may be this leg. And ping pong. And then a few people. And this one, we do have a significant artifact of this individual's leg is actually in between the other two here. So that limb looks like it may have been missed.